Hi everyone, I'm Aditya and today I'll present neural attention fields, which was done in collaboration with Kashyap and Andreas at the Autonomous Vision Group. So consider these three driving scenes shown here, which are rendered using the Carla simulator. On the left, we show three RGB images describing the scene in perspective view. And on the right, we show the bird's eye view semantic segmentation map, which is an alternative representation of the same scene. In this representation, different colors represent different semantic classes. For example, blue represents obstacles, purple represents road, and red and green represents different traffic lights. The bird's eye view space is very well aligned with the 3D space in which the vehicle drives. So this kind of representation is very suitable for the task of trajectory planning and driving. So several recent approaches such as learning by cheating and Roach have exploited this bird's eye view semantic segmentation representation to train driving policies in a two-stage manner. In this pipeline, a teacher model is first trained using the bird's eye view semantic segmentation map as input, and then it is used to supervise a student model which drives from camera inputs alone. An alternative paradigm is a single stage learning paradigm in which the bird's eye view semantic segmentation map is predicted as an auxiliary task along with the main trajectory planning task. In this work, we explored this paradigm and propose an efficient way to predict bird's eye view semantic segmentation map. Our model takes 2D image patch features as input, and it compresses it into a single vector by computing an attention over these patch features. For this, we assume a uniform attention prior in the beginning. Next, we use our model neural attention field, which is a multi-layer perceptron, which iteratively refines this attention map to focus on the areas which are relevant for any location x, y, t in the bird's eye view space-time volume. Here, x and y represents the spatial coordinates related to the ego vehicle position in the bird's eye view space, and t represents the temporal coordinate relative to the current time step. By using this implicit representation, we can compute cross attention between a vector in a continuous space and a discrete set of tokens, which is different than how transformers are currently used. We apply this process for a certain number of iterations. And after n iterations, we get the aggregated feature map Cn, which we use to predict semantic classes for any point x, y, t. And in addition, we also predict the waypoint offsets, which is a 2D vector which points to the location where the ego vehicle is present at any time t. Once we have predicted these waypoint offsets we can extract the trajectory from them, and then we pass the extracted trajectory to the PID controller, which outputs the final control for the vehicle. And this allows us to predict the semantics and waypoint offsets at any arbitrary resolution and in a compact manner with a constant memory footprint. So here is a qualitative example of NEAT's driving capabilities. So on the top right, we show the predicted trajectory in the red curve and the goal waypoint in blue. And the bottom right, we also show the predicted bird's eye view semantic segmentation map. Quantitatively, we compare our method against the bottom two approaches, which are imitation learning approaches, which do not use our representation. And the top two approaches are two-stage distillation-based approaches, which use bird's eye view semantic segmentation as input. And we observe that our model performs better in terms of infraction score, which shows that it drives safely compared to them, and it leads to fewer collisions. Here is qualitative comparison of our model against some common imitation learning baselines used in Carla. So CLRS ends up deviating from the route and is not able to complete successfully. AIM-MT gets blocked outside lanes due to understeering, whereas learning by cheating gets stuck at the intersection and is unable to complete the route. In contrast, our agent is able to successfully navigate the intersection without any collisions and is able to complete the route. So thank you for listening, and you can come to our poster for more details. Should I start?
Yeah.
Yeah, hi. So my presentation is about our paper, box attention for 2D and 3D transformers. So it presents box attentions as a lightweight attention mechanism. Boxer 2D for 2D object detection and segmentation. Boxer 3D for 3D object detection. Our box attention is motivated by the sliding window in modern detectors. So it utilizes the grid structure within boxes in attention computation. Yeah, so in box attention, each query vector is assigned a reference window with the query position at its centers. Instead of using image features as key vectors here are learnable embeddings, which represent relative position of the grid structures. The value vectors are sampled from the reference window. So in the attention computations, the attention map is computed by computing the dot product between the query and learnable embeddings. The attention map are then combined with the sample values to produce the attended features. So besides, our box attention is equipped with a where to attend module. The idea is to transform the original reference window to a transformed window. So it allows box attention to learn where to attend during the training procedure with the learnable transformation, translation, and scaling. We also extend box attention to take the value of the multi-scale feature maps. In this case, we place the reference window to the query features across multi-scale feature maps. The where to attend module is also work with multi-scale feature maps. So each query vectors is assigned a reference window of the different size based on the multi-scale feature maps here, and it projected into different feature maps. So with the box attentions, we design Boxer 2D for 2D object detection and segmentations. Boxer 2D takes the multi-scale feature map of ResNet as its input. So in the encoders, we assign the reference window of 32 square to 256 square to the features of the C3 to C6 respectively. In the decoders, we use the bounding box proposals corresponding to the encoder features as the reference windows. And our predict a bounding box with respect to a reference window. We can see here Boxer 2D generate the high quality object proposals, which highly overlap with the predictions. Moreover, our visualization of the predicted box from encoder attention modules shows that it can capture reason of different aspect ratios. In order to work with 3D object detections, we extend box attention with rotation transformation to predict the rotated bounding boxes. So now where to attend module contains 3 basic transformations: translation, scaling, and rotations. We show the behavior of Boxer 3D. So the lab image shows its predictions for the vehicle category denoted in the green boxes. And for the right image, we show the boxes of the box attentions in multiple heads. We can see here that box attention can capture the box of different angles. Here we show the comparisons of Boxer with other methods on the COCO detections. Our Boxer 2D outperforms other methods across ResNet 50 and 101 and in all metrics. And we can train it with short training schedules. It's the same trend in the instance segmentations. We outperform convolution-based and transformer-based in all the metrics. And for the 3D object detections, Boxer 3D achieves a compelling result in the vehicle detections. We also set up a naive experiment in which the deformable data is used. And we can see here, Boxer outperforms deformable data, especially for small object detections like pedestrians. Yeah, we show some of the visualizations of the Boxer 2D in a crowded scene. So without any handcrafted modules, it can still detect correctly. Same with the 3D object detections. It can predict the vehicles with a high accuracy. Yeah, thank you for your attention. And if you are interested, please visit our poster.
In this talk, we are going to present a transformer-based approach for monocular depth estimation with our novel simplified attention modules. We propose a self-supervised depth estimation model with simplified transformers called DEST in short. DEST is largely structured with a DEFnet encoder, a DEFnet decoder, and a postnet. The encoder and the postnet are stacked with our novel simplified transformer blocks, and decoder decodes features in a progressive manner with skip connections from the encoder. DEFnet produces a view synthesis based on current frames and learns to estimate depth based on the photometric loss between the JSON frames and the synthesized images worked by the post as a training objective. As a final product, a trained depth network is only needed for inference. We allow connections among the transformer blocks of DEFnet and joint transformer blocks of postnet. Each transformer block is equipped with one overlap patch embedding layer and repetition of attentions and mixed FFN layers. For joint attention, output features of each transformer block from DEFnet are inputted along with the features of postnet to perform joint attention. Our simplified attention module overcomes conventional transformer structures overhead of quadratic computational complexity during matrix multiplication of query Q, key K, and value V with respect to the input sequence length represented as n in this slide. For dense image prediction where often high-resolution images are used, this has become the major bottleneck as the computation grows with n squared. We firstly mitigate this issue by reducing spatial size of feature maps through additional 2D convolution operations. We also replace softmax with row-wise max pooling to get rid of the computation costs in softmax and reduce the memory footprint with output size of n by 1. We perform a column-wise average pooling on the input feature, resulting a V of 1 by C. The output of the attention module remains at n by C, but the intermediate computation and tensor size are greatly reduced. For simplified joint attention modules, reference features from the transformer blocks are utilized when computing the product of Q and K, and the value features extracted from neighboring frames are utilized for the final attention multiplication. Most implementation of transformer-based networks require layer norm, which computes statistics of inputs on the fly, and this imposes additional computation overhead for inference. Batch norm, on the other hand, uses the accumulated statistic from training and avoids such computation in the inference. Simply replacing existing layer norms with batch norms would cause the training to diverge. We empirically found places to apply batch norms to a newly placed or to replace original layer norms. With the aforementioned improvements, our best model DEST-B3 performs the best among the relevant methods with much smaller model size and reduced complexity. Also, connectivity between the DEFnet and the postnet improves the performance, showing that joint learning of DEFnet and postnet helps improving depth estimations even more. Here we compare our DEST model with one of the current state-of-the-art methods, PACnet. We compare the latency in the original PyTorch framework as well as latency using TensorRT on NVIDIA A100 GPU in both FP32 and FP16 precisions. Compared to PACnet, DEST is significantly faster, particularly showing a great speedup in inference. Our model in FP16 achieved the lowest latency of 8.87 milliseconds, reaching 57% speedup compared to the current state-of-the-art method. The qualitative results also show that the test performs depth estimation with more sharp edges, also predicting depth of the objects that are far. We further examined the performance of DEST in semantic segmentation task. We mainly compare our method against segformer based on two model sizes, one small-sized and one medium-sized. Our model DEST outperforms segformer with much lower model complexity and latency for segmentation vision tasks as well. Thank you for listening to our achievements. More details can be found in our paper.
I will press it and you can go ahead.
Okay, thank you. We present a novel transformer-based approach for instance segmentation of 3D point clouds. Our approach, called Master-Former 3D, predicts accurate 3D instances via iteratively refining instance queries. Our method is in stark contrast to conventional methods, which mostly rely on the voting and grouping paradigm. Here, each vote votes for its instance center. As votes from the same object are now closer to each other, this paradigm subsequently groups these clusters in order to generate instances. This paradigm is adopted by many top-performing methods for 3D instance segmentation. They leverage a center voting branch to predict the corresponding instance center of each point. Subsequently, votes are aggregated using sophisticated grouping modules. We now take a closer look on soft group, which represents the current state of the art for 3D instance segmentation. Here, we show a single U-shaped table. We observe that the center votes of soft group significantly differ from the true instance center, depicted as a red big point in the middle. As the center votes are widely spread in the scene, the grouping stage consequently fails and outputs multiple instances. Next, we show that voting and grouping-based methods are sensitive to the choice of clustering hyperparameters. We observe that the center votes constitute a single dense region. Using soft groups clustering parameters, we cluster all center votes into a single instance. Soft group's refinement module suppresses the instance proposal. Adapting mask to former, an excellent work for 2D image segmentation, we propose a transformer-based model for semantic instance segmentation of 3D indoor scenes that addresses the aforementioned problems of voting and grouping-based approaches and sets new state-of-the-art scores on the challenging ScanNet benchmark. Our model predicts instance queries that encode semantic and geometric information about each instance in the scene. The key idea is to compute the dot product between instance queries and every point feature. This results in instance queries heat maps over the entire point cloud. We now discuss the overall architecture of Master-Former 3D. We obtain strong multi-scale point features from a sparse convolutional backbone. At the core of the model are instance queries, which each should latch onto one single instance in the scene and predict the corresponding instance mask. To that end, the instance queries are iteratively refined by the transformer decoder, which allows the instance queries to cross-attend to point features extracted from the feature backbone and self-attend the other instance queries. This process is repeated for multiple iterations and feature scales, yielding the final set of refined instance queries. A mask module consumes the refined instance queries together with the fine-grained point features and then returns for each query a semantic class and a binary instance mask based on the dot product between point features and instance queries. After thresholding to a binarized mask, we obtain instance masks on multiple scales. We mask out the context from the cross-attention. Moreover, after the final binary thresholding, we obtain a per-point instance mask on full resolution. We now compare mask to form a 3D with soft group on the previously shown scenes. This is the heat map associated with the table. We see that it has high confidence over the full extent of the instance, which results in a correct prediction. Here we show the example with the 8 chairs. As we do not rely on any grouping stage, we are more robust against instances of the same class placed next to each other. Overall, mask to former 3D shows very promising results. We have shown that the mask to former architecture is a generic approach that can, with a few modifications, be applied to the task of 3D instance segmentation, setting new state-of-the-art scores on the challenging ScanNet benchmark. Thank you for watching.
Hi everyone, I'm Romain Loiseau and I'll present you the work we did with Mathieu Aubry and Loïc Landrieux entitled Helix 4D, online segmentation of LiDAR sequences. The idea of the paper is to look at LiDAR data as a continuous data stream and to process the data slice by slice without waiting for a full rotation to be acquired. Our model Helix 4D, which is accuracy on par with the best segmentation algorithms, with a reduction of over 5 times in terms of latency and 50 in model size. To precisely assess the real-time readiness of LiDAR segmentation methods, we also introduced HelixNet, a 10 billion points dataset with fine-grained timestamps and sensor rotation information. Real-time analysis of 2D data sequence is crucial as LiDAR sensors are becoming ubiquitous in autonomous driving. However, rotating LiDARs have a very complex acquisition geometry, as the sensor is rotating at the top of a moving vehicle and the scene moves around the sensor. In order to have consistent inputs across time, most methods split the acquisition into sensor rotations and then processes them using either range images, 2D polar grids, or 3D partitions. Doing that, they have an unavailable latency of 100 milliseconds, which corresponds to the rotation frequency of the sensor. This latency corresponds to 1.5 meters at 50 kilometers per hour, which is prohibitive for autonomous driving. And we have to add the inference time to get the full latency between the acquisition of the first point of the rotation and the prediction of its label. We understand that this is a difficult challenge, as the number of acquired points often results of prohibitive latency for autonomous driving. Our method takes the complex spatio-temporal structure into account. We propose to split the acquisition into slices of rotation, resulting in a much smaller acquisition latency. Designing an efficient network, we provide real-time online semantic segmentation. To leverage real-time semantic segmentation for autonomous driving, we present an efficient spatio-temporal transformer. Our proposed spatio-temporal transformer derives from the cylinder 3D architecture that processes full rotations of the LiDAR sensor by performing a unit-style 3D convolutional neural network on a 3D cylindrical grid. We simplified this architecture at its most so that we have an efficient pipeline and propose to process the data slice by slice. At the innermost layer, we use an efficient sparse spatio-temporal transformer that performs attention on voxels from both current and past slices with a learned relative positional encoding. It allows for the architecture to gather information on a large 4D spatio-temporal receptive field, while remaining efficient as the encoder is performed only once per slice. And we keep previous keys and values in memory to be efficient. With this architecture, we achieve state-of-the-art performances with a reduction of over 5 times in terms of latency and 50 in model size. We evaluate in both the frame-by-frame setting and the setting with slices of 1/5 of a rotation. We see that while our model is comparable to state-of-the-art on the frame-by-frame setting, we leverage real-time LiDAR semantic segmentation by conserving the same performances when reducing the slice size, while always having inferences time accordable with real-time setting. Looking at the results for all slice size, we see that Helix 4D is as accurate as the largest and slowest models, with an inference speed comparable to the fastest, less accurate models. We can explain that with the larger spatiotemporal receptive field used in the transformer. Alongside the method, we also present a new public dataset for online semantic segmentation that contains 10 billion annotated points across 6 French cities in various urban settings, with crucial pointwise information allowing for realistic slice splitting and online inference simulation. This dataset is available publicly. To conclude, we presented both a dataset designed for methods real-time readiness assessment and an efficient spatiotemporal transformer architecture specifically designed for rotating LiDAR sequences. We showed state-of-the-art performances for semantic segmentation with a reduction of over 5 times in terms of latency and 50 in model size compared to others. The implementation and the datasets are publicly available on the paper webpage. Thanks for your attention.